In this video, we're going to learn how to make a vector loop diagram and derive the equations for a kinematic mechanism. Step 1 is to assign a coordinate frame. You want to attach the coordinate frame to a fixed point. So in this case, that would be the ground. So we could put it on either the left ground point or the right ground point. Really, these are all connected. So it's basically like this whole thing is ground. And also normally we'll put it along, the X direction goes along the ground. So we'll have X like this, and then Y goes perpendicular. Now, even if the ground was not flat, you could still put X along the ground. It ends up making the math easier. So then step 2 is to assign a vector to every link. Basically, you'll just want to connect the dots with arrows. The direction of the arrows does not matter. What's going to be important is if we write the equations to match the diagram. So each of these arrows needs a label, so we'll number them. Say ground is R1, the crank, which is the input, is R2. The coupler then is R3, and the output rocker is R4. Now we could have named these in any order or put the arrows in any direction as long as we just connected the dots of all the joints. So then the third step is to write the vector loop. So we have to go around the loop in one direction. We can either go clockwise or go counterclockwise. So if we go clockwise, then we'll start at the origin and we'll go along R2, so that will be positive, along R3, so that's positive. Then we go against R4, see we're opposite the arrow direction, against R1, opposite that arrow direction. And all those added up will equal the 0 vector because we ended up the same place as we started at. So writing that equation, we'll have R2 plus R3 minus R4 minus R1 equals 0. So notice that the equation matches the diagram in the direction that we went around. Now we could go around in a different direction. Let's pretend if we go around counterclockwise, what would that equation look like? Basically just all the signs would change because we would go in the forward direction of the arrows for R1 and R4 and in the reverse direction of the arrows for R2 and R3. So that would look something like this. R1 plus R4 minus R2 minus R3 equals 0. And you see these equations are both correct. It just depends which way you went around the loop because they both add up to 0. Now think about basically if you just moved all of the stuff on the green equation to the other side, then you would get the blue equation. So those are equal. The fourth step is actually to break these into position scalars. So for the vector loop equation, we'll get an X and a Y. So let's go with a green equation. So for that one, in the X direction, we will have cosine components, and in the Y direction, we'll have the sine components. And we'll use this abbreviation. For example, C1 equals cosine theta 1, S2 equals sine theta 2. So you can see how that abbreviation works. Now, we need to actually know what those angles are. Every angle is given positive counterclockwise relative to the positive x-axis. So just like in a normal coordinate frame. So that would look something like this. Theta 2 goes there. Theta 1 is just 0. Theta 4 is like that. And then theta 3 remember it goes from the positive x-axis, so measure from the horizontal, just like that, theta 3. Okay, so if we break these up into sine and cosine components, then we'll have R2 C2 plus R3 C3 minus R4 C4 minus R1 C1 equals 0. And then R2 S2 plus R3 S3 minus R4 S4 minus R1 S1 equals 0. And now looking at this, we can actually simplify it some. So R1 is along the ground, so theta 1 is just 0. Well, cosine of 0 is 1, and sine of 0 is 0. So we can do some simplification here. If sine of 0 is 0, then this term goes away. And if cosine of theta is 1, then you just have the minus R1 there. So step 5 is to identify knowns, unknowns, inputs, constraints. So knowns are constants. So that is anything that you can measure at the beginning and it doesn't change, things that you would actually know. So let's make our list of knowns. So what's constant here? Well, all of the link lengths, so all of the R values are constant. And then the only angle that doesn't change is theta 1, the ground angle. So theta 1 is also known. Now, unknowns, those are values that change with time. So anything that's not a constant, that's going to be changing, it's something that we'd have to calculate. So that is the other stuff, theta 2, theta 3, and theta 4. But we need an input. And for this, we actually get one input because this mechanism has 1 degree of freedom. So the number of inputs equals the number of actuators. So this is easy to tell what is the input if you can see it physically on the mechanism. So like if you can see a hydraulic or pneumatic cylinder, or if you see a motor, that's definitely the input. Now in this example, there aren't any, but the typical convention is to go with theta 2, the crank angle on the left side being the input. So we'll say input is theta 2. So now we have 2 unknowns, theta 3 and theta 4, and 2 equations, x and y. So at this point, we would be able to solve. This mechanism does not have any constraint equations. Constraint equations are usually angle relationships that you can get from if there's a link that is more than just binary. So if it's a ternary link, then it will have a constraint with multiple vectors related by a single angle. So that will allow you to solve for more than 2 unknowns. But in this case, we don't have any constraints, so we can just go ahead and solve.